Hey guys! So today we're going to talk about applications of quadratic equations. So this is actually one of my favorite topics because you guys are always asking me questions like, when are we going to use this math in real life? Well, today we're going to talk about it. When you're going to use quadratic equations and all of what we're talking about in math in real life. Okay, so that means we're going to talk about word problems, which you guys love, and when we do the math in real life, the math never comes out pretty. It's always got kind of ugly answers because everything in real life is not perfect. All right, so just keep that in mind as we're working through this. Okay, so you should have your page 16 handout, okay, the notes, and before we get to it, let's kind of talk about quadratics. So with quadratics, right, we have this shape, okay, it opens up, and we also have this shape where it opens down. So can you think in real life a certain scenario in which something was either it could be dropped or something that would take this shape or would take this shape? Can you think? So let's talk about this shape opening up for a second. Have you ever heard of there's a certain bird and it actually dives down into the water to catch a fish? So you would have like a lake or ocean or whatever, and then you'd have this bird, there's my bird, flying in, and it would dive down and catch a fish and then swoop back up. So a quadratic equation could mimic the flight path of the bird. You could also think about a person or an animal diving, like in water, right? You could have an otter or a dolphin or something diving down into water underneath and then coming back up to surface. There's a couple of other scenarios, but that's enough for that one. What about this shape, the upside down one? This one is a famous shape for sports, right? When you're throwing any sort of ball, baseball, basketball, anything like that, and you throw it and it hits the arc and then it comes back down. Okay, so sports is famous. Also shooting a gun, right? And the path that the bullet could take, that could be that. Let's see what else. I can't think of anything else. What about fireworks? So you light it and it goes up into the air, it explodes, and then eventually all the debris comes back down. So that's another example. So this is what we're talking about today, applications of these quadratic equations. So let's go ahead and get to the notes that we're talking about. And let's go ahead and read through this. This is about Acme Fireworks, and you are, I guess, being employed. So let's see what we got. So it says the Acme Fireworks Company has been engaged to provide the fireworks for the annual 4th of July fireworks show for the town of Madison, Georgia. Okay, cool. The city manager of Madison selected Acme Fireworks because they have 4 different kinds of fireworks. All right. Each firework is designed to explode when the rocket reaches its highest point in the air. Okay, so that's important to know. So what I would do is I would underline it. Okay, so I would say, all right, it explodes. So I would circle explode, and then I would underline when does it explode? When the rocket reaches its highest point in the air. Okay, let's keep reading. Once the rocket explodes, the sparkles of different colors fly out of the rocket and stay in the air for the same number of seconds as it took for the rocket to reach the highest point. Okay, so I'm going to go ahead and circle sparkles. So we got sparkles. They stay in this, so I'm going to underline this part. They stay in the air for the same number of seconds as it took for the rocket to reach the highest point. Okay. All fireworks are launched from the ground. That is important to know, from the ground. Okay, this other stuff makes it complicated, so we're actually just going to ignore it for our purposes. Okay, so just ignore all of this talking about the wick burning and all that. Okay, we're not going to take that information into consideration for our very first problem talking about quadratics. Okay. All right, so the city manager has visited your classroom to ask your class to confirm the figures that Acme Fireworks Company has given him. Specifically, he wants to know, okay, what does he want to know? So this is important. He wants to know the height at which the rockets will explode, okay, and how long, okay, so how long the sparkles for each type of firework will be in the air. Your teacher is interested in the method that you choose to solve each equation. All right, so below you are given the equation for the flight of each firework. For each brand, tell the height of the rocket when it explodes, how many seconds it took to reach this height, how long the sparkles remain in the air. Okay, this right here is important. In each equation, X stands for what? The number of seconds the rocket is in the air. That's important. X is time. Okay, X is time. In seconds specifically. So I'm going to say time, but specifically S in seconds. And F of X. You remember F of X is a fancy name for what? Yep, Y. So Y is what? The flight of the rocket in feet. Okay, so it is flight. So I'm going to say Y is, it's the height of where the rocket is, and specifically where it is from the ground in feet. Okay, now that we have all of our base information, let's go ahead and look at the first type of firework. So I scratched out blue bombers because that equation actually really didn't work for this scenario. So let's go ahead and look at number 2. This type of firework is called red rockets, and its flight path is modeled by g of x equals negative 2x squared plus 29x minus 90. All right, so first of all, one thing that I can tell from this equation is my a value. You see that a value? It's negative. So what does that mean about the flight of this firework? Does the quadratic open up or does it open down? Yep, it opens down. Okay, so I'm going to draw me. Here's my firework. Let's go ahead and here's the ground. All right. Okay, so I want to know how high is the rocket when it explodes? How high is it when it explodes? Okay, so do you remember from up here, it talked about when it exploded. It explodes when the rocket reaches its highest point in the air. Highest point in the air. So for this one, where is the highest point in the air? The highest point in the air would be right here, the maximum. Okay, so this specific point, though, is called something else. Not only is it a maximum, it is my vertex, right? It's my vertex. So with my vertex, I have an x-coordinate and a y-coordinate. So in the equation, it talked about what the x and the y was. So let's review that. X is the time in seconds. Y is the height in feet. So x is time, y is height. So let's go ahead and write that so we remember. So x is time, y is height of the firework. All right, so if time is going this way, right? So over here would be time 0, and then over here would be however long it took. And then height is your y-axis. So this is at 0 feet because it's on the ground, and this would be at however tall this one is. So we need to know this vertex point. That's kind of important. Okay, well, what form is this equation given to us in? It is in standard form. So how do you find the vertex from standard form? Do you remember? You got to use x equals negative b over 2a. All right, that was from Monday. You have to use that in order to find the x value of the vertex. So let's go ahead and just plug in what we know. So I need negative b. So b is a positive 29. So plugging in a 29 all over 2 times my a value. My a value in this case is a negative 2. Okay, so I got negative 29 on the top divided by a negative 4 on the bottom. So a negative divided by a negative is a positive, but 29 over 4 is not going to come out even. It's actually 7.25. And this was my x. Okay, so what is x? Is it time or height? It's time. So this is in seconds. So what does that mean? 7.25 seconds. Well, right here is when the firework exploded. So from here all the way to here was 7.25 seconds. That's what that means. Okay, so I'm going to go ahead and label this. So this is 7.25 seconds. Okay, but the first question is, how high is the rocket? Okay, well, that's seconds. That's how long it took. So I need to know how high. So that means I need the height, which is the y value of the vertex. So let's go ahead and find the y. How do you find the y? Remember, you plug it back into the original function given to you. So y equals negative 2 parentheses x, which we got 7.25. And then there's a squared plus 29 times 7.25 minus 90. All right, so I'm just going to throw all this in my calculator at one time. So negative 2 parentheses 7.25 squared plus 29 parentheses 7.25 parentheses minus 90 equals, I'm getting 15.125. Now, what's our unit on this? This was height, but the height, remember, was measured for this scenario in feet. Okay, so that means this firework from the ground to where it exploded was 15.125 feet high. Okay, so now we can go ahead and answer these questions. How high is the rocket when it explodes? Well, it was 15.125 feet high. 15.125 feet. You've got to put the unit, because if you just say 15.125, is that in inches? Is that centimeters? Is that miles? In meters? We don't know. You have to tell what is it measured in. It's measured in feet. Number 2, how many seconds was the rocket in the air before it exploded? Okay, so that means at time 0, from when it left the ground all the way until it hit the vertex, how long did that take? Well, the x value of that vertex is measured in time. So at time 7.25 seconds, it exploded. So that means it took 7.25 seconds in order for it to explode. So it was in the air for a little over 7 seconds. Okay, number 3, how many seconds did the sparkles stay in the air? Well, if you remember from up here, it talked about the sparkles and we underlined